g is the function from R to R, and x is the random variable. So we compose these two functions, and the outcome of that is again a random variable. So for that random variable, we have studied this probability mass function. And to find that probability mass function, what essentially we are going to do is we are going to find for each small y, that is a real number, y is a real number, we need to find all the possible values of x, that is the solutions of the equation gx equals to y, all x in the domain we will find for that gx is y is the given real number, and for those x we will find the probability mass function of the original random variable capital X, and then we add these things, right? This add all for the all possible value of x. If we sum all this probability of capital X equals to small x, that is exactly the probability of capital Y equals to y, right? So this we already know. So we know how to find the probability mass function of the random variable g of capital X. That is the last class, and we have discussed many examples: binomial random variable, normal random variable composed with the sine function, and other several examples. This was the main main result which we use in the computation. That is the we need to find all the roots of gx equals to y, and using the derivative we have found the probability mass function of the new random variable capital Y, which is g of x. So we have discussed the linear case and the quadratic case, and in the last class we studied expectation formula. We studied the expectation formula. So expectation we defined as in two different cases. Every time we have two different cases: random variable is discrete or random variable is a continuous, right? Depending on what is the range of the random variable. So we have defined the expectation of given random variable to be this quantity whenever random variable is discrete, and in terms of integration whenever the random variable is continuous. And both of these expectation holds we can find whenever the this corresponding series is absolute convergence. And we have discussed that we will not worry about the absolute convergence if our random variable takes all the non-negative values, right? All the non-negative values. So we'll check the absolute condition only when it takes the at least one negative value. So we have found expectation of different random variable in the last class, starting from this first example where that is exactly the relation between expectation and mean. So mean is the average of 0 and 1, that is half, and that is coming out to be the expectation. So this example gives us the idea that what we are doing here in this course is actually the generalization of the usual standard mathematics which we studied in school, where we have the uniform random variable with finitely many outcomes. Right? So expectation we have discussed in the last class. In today's class we are going to discuss the variance. And to define variance, we will use the expectation of different random variables. So we discussed in last class. Let us recall what is the expectation of which random variable. So binomial random variable expectation we computed, that is n times p, where n is the number of tosses and p is the probability of success. And for Poisson case, the mean was lambda, where lambda is the given parameter. For exponential, it is inverse, so 1 upon lambda. And for geometric, so that essentially we are going to use in today's class also. So it will computed geometric case, that is 1 by p, right? So I'm not able to find. Yes, this one. So that is 1 upon p, right? So whenever we have a geometric random variable in terms of p, the expectation is 1 by p, that is mean. So we will require the expectation to find the variance, because variance definition depends on mean in every random variable. So whenever we are asked to find the variance, first thing we need to find the mean. So we'll see the actual definition in the today class. So in the last class we discussed expectation of random variable capital X. Today we start with the definition of expectation of the random variable g of x. So we start with that, and then we'll move to the definition of variance. So let us start with the first result. So we start with the discrete random variable. Let x be a discrete random variable, and we have the function from R to R. We have the function from R to R. So what is the formula of the expectation of g of x? What is the formula of the expectation of g of x? So expectation of g of x we can directly define using this formula. So we can consider g of x as a random variable capital Y. So in that case, the direct formula of the expectation gives expectation of capital Y is equals to summation of small y belongs to the range of capital Y, and this will be small y times the probability mass function of capital Y at small y, right? So by definition we'll get that, but what we are going to show in today's class is the expectation in terms of the probability mass function of x, in terms of probability mass function of x. So that is summation x belongs to range of x, g of x, f capital X at x. So using the all possible values in the range of the first random variable, we'll going to find going to show that the expectation of g of x is exactly this quantity. And again here also we have the condition that expectation exists if we have the absolute convergence. So absolute convergence condition is modulus of these, and modulus of this is always non-negative, so that is exactly modulus of gx, right? Summation modulus of gx times fx. So this equals to this whenever summation all the possible values of the range modulus gx times fxx is finite. Okay, so proof is quite simple, and it uses the probability mass function definition of the random variable capital Y. So what is the probability mass function? So we started with that. So we are going to use this this equation, right? So using this equation, we just substitute. That is the proof. So by definition, what is expectation of g of x? So here capital Y is the new random variable gx. So by definition of the expectation, what is this value? This value is all the possible values in the range of y. In the range of y, we have y, fy at y. Okay, so by definition of expectation, the expectation of this new random variable gx is this quantity, right? Is this quantity. Now we substitute this formula. We'll substitute this formula. So what we'll get is this equals to summation y belongs to range of gx y times probability of y equals to y. And probability of y equals to y, we know that all x such that gx equals to y, probability of x equals to x. All right, so we substituted this value. And what are the all possible values of y? So we started with summation over y. Y is each value of the range of the capital Y of gx function, but each value in the gx comes from x. Right? So if we add all the possible y in values y in the range of y, we have all the pre-image of that for each value. So that means summation of all such x is essentially the domain of x. Is essentially the domain of x. So we substitute y equals to gx, so that will give us summation gx probability of x at x, and the summation is over all the possible values in the range of x. Okay. So what is this quantity? This is nothing but all x in the range of x such that gx into fx at x. Okay, so this is essentially the equation which we wanted to prove, that the expectation, whenever we want to find the expectation, we already by assuming that we already know the probability mass function of the random variable capital X, if you know all the possible value of gx in the range of x, there we just substitute and find it. Okay, so let us take one example so that we can. So what is the continuous case of this? Continuous case is expectation of gx is, instead of summation, we have integration. So let us take one example of the continuous case of the continuous case. So we discussed the standard normal random variable. We know it's a density function. So let x2 be the normal random variable, which is standard normal random variable, and we define a new random variable, that is maximum of x and 0. So question is find the expectation of y if it exists. So the normal random variable is a continuous random variable, right? It is a continuous random variable. So what is the range of random variable capital X? Minus infinity to infinity, right? Because we know the graph of that is bull shape, right? So it starts from minus infinity, it goes up to infinity. Like if you have a uniform continuous random variable, then it is defined on the whole real line, but it is positive on the interval, but it is defined on the whole real line. So outside interval, its value is 0. So this is a random variable which is defined for all values between minus infinity and infinity. So if we take the maximum of x and 0, so this is our gx function, right? So let us write down that. So here our function gx equals to maximum of x and 0, and x is any real number. So what is this function? So when we take the negative value, what is the maximum? That is 0, right? So whenever x is negative, the value of the function is 0. And if x is non-negative, then what is the value? That is x. So x is maximum on the right side, right? So x is maximum. So this is our gx function. Because why we are finding gx? Because we need to substitute in this formula. So first thing we need to find gx, and the second thing is probability mass function. We already know probability mass function of the normal random variable, right? That is 1 upon square root 2 pi e power minus x square by x. So also fx at x is 1 upon root 2 pi e power minus x square by 2. So that is the density function of the standard normal random variable, right? Standard normal random variable. So what is now we can find what is the expectation of y, that is minus infinity to infinity gx fx x dx. But since gx is 0 on the negative side, on the negative x-axis, its value is 0. So 0 times anything is 0, right? 0 times fx is 0, whatever fx is there. So that means we need to integrate only on the positive x-axis, only on the positive x-axis. And positive x-axis will substitute this value and this value, multiplication of these two, gx and mass function, gx and the density function. So that is integral 0 to infinity. Value of gx is x, and the value of this function is 1 upon root 2 pi e power minus x square by 2. So we know that this function has antiderivative. So we just find the antiderivative and substitute the limit because it is a continuous function. So antiderivative, we know that is minus x square by 2 is the antiderivative, and the limit is 0 to infinity. So when we substitute infinity, e power minus infinity is 0, right? Because exponential is increasing function. So e power x goes to infinity as x goes to infinity, right? So therefore the upper limit is 0. The lower limit x at 0, the value of the function is minus 1. But it is a lower limit, so it will come with the minus sign. So that is minus of minus 1 is 1. So 1 times 1 upon root 2 pi, that is the answer. Right. So whenever we are given some function g of x, which is a function of random variable. So what is gx here? Gx is maximum of x and 0. So capital X is our random variable. So it is a function. It is defined at each outcome, and maximum of x and 0. That means 0 is also a random variable, which is a constant function 0 at every outcome. Right? It is a constant function. So capital Y is, so we are given a random variable. We can find, using this example, we are finding a new random variable. Given x, we get y, which is a random variable. Right. So this is gx. So for different types of random variable, we can get different examples. And x is given, we can find 2x plus 3, which is a random variable. X square is a random variable, right? Any linear combination is a random variable. Any power is a random variable. Inverse power is also random variable, 1 upon x, right? If x is a random variable, it is a real valued function. 1 upon x is also real valued function. Only thing we need to check, the denominator should not be 0, right? So for all such functions, capital Y, we can find its expectation whenever it is convergent. So here again, we have not checked the absolute convergence because what is the range? Range is 0 to infinity, but we are taking maximum function, right? So what did you say? I didn't listen. You said 0 to infinity, right? Okay, so then it is correct. So range of capital X is minus infinity to infinity, but as you said, is correct that range of the capital Y is 0 to infinity. Okay, so so now we know how to find the expectation of continuous random variable and the discrete random variable, continuous and discrete. But we have also discussed some examples of the mixed random variable, that is a linear combination of two random variables, right? One is discrete, the other is continuous. So we want to see what is the expectation of mixed random variables. So mixed random variable is always a addition of two functions. One function is continuous random variable, and the other function is a staircase function, which is known as the step function in mathematics. So any whenever we say mixed random variable, that means it is a addition of two random variables. So mixed random variable capital Yx is a addition of two random variables so Cx and so what is this? This is CDF cumulative density function of mixed random variable capital Y is addition of two random variables, that is Cx and Dx, where Cx is continuous. What we are saying actually is that C is continuous random variable and D is discontinuous random variable, that is, so this D function is discontinuous. So we say that CDF of a random variable is discontinuous. That means its probability mass function is non-zero. So it is not left left continuous, and the difference between value of the function and left limit is positive. So that is a probability mass function. So that is at points y1, y2, yk, we have probability of y equals to yk is positive. Probability of y equals to yk is positive. Okay, so what this gives is let the derivative of Cx is small cx at each point x where C is differentiable. So what is capital Cx? Capital Cx is CDF of a random variable. CDF of a random variable y. Y has two parts, Cx and Dx, right? CDF of y has two parts. One is a continuous part, other is a discontinuous part. So at points where it is discontinuous, the probability mass function is positive. Where it is continuous and differentiable. It's so this is a derivative of the CDF, so that is a density function, right? That is a density function at continuous points where it is differentiable. So what we mean here is that integration of the density function is 1 when we have the continuous random variable, and at each point where it is discontinuous, if we add all those probabilities, that is 1 if the random variable is discrete, right? So if you have a discrete random variable, we have this the probability density function equation is this equals to 1. If you have a continuous random variable, the total probability is 1, right? But now we have a mixed random variable. That means we have continuous part and the discontinuous part, where each yk is the point of discontinuity. So whenever we have such a random variable and this is its probability density function, what is the expectation formula? So we know the expectation formula of the continuous variable and the density variable. So here the expectation of this random variable is defined as integration x cx dx plus summation yk probability of y equals to yk. So this is our expectation formula of the mixed random variable, Okay. So let us take one example. So let x be a mixed random variable such that its CDF is given to us, that is capital Fx is equals to 0 over the interval on the negative x-axis. Its value is half whenever we have 0 less than equals to x less than 1. Its value is x by 2 over the interval 1 to 2, and for x greater than equals to 2, we know the last value of CDF is 1, right? It starts from 0, it goes up to 1. What are the property of CDF? It is a monotonically increasing function, right? It starts from 0, goes to 1, and it is defined over the whole real line, over the entire real line. So this is the CDF of some random variable x, which is a mixed type. So why it is a mixed type? Because what is the reason? It is continuous over certain part, it is discontinuous over certain part. That means there are points where it is discontinuous. So at x equals to 1, is it so over the intervals it is continuous, right? These functions are continuous. Over the intervals it is continuous. We need to check at the endpoints. At x equals to 1, the right limit is 1 by 2. That is the value 1 by 2 at 0. At 1. The left limit is half. The value of the function at x equals to 1 is half. Similarly, the left limit at 2 is 1, and the value of the function at 2 is also 1. So that means it is left continuous at 1 and 2, right? But we can see that it is not left continuous at 0, because left limit is 0 and the value of function at 0 is half, right? So over this interval from 0 to infinity, it is continuous. Up to 0 also it is continuous, minus infinity to 0. But at 0 it is discontinuous, right? At 0 it is discontinuous. So therefore it is a mixed type random variable, and total probability should be 1. Total probability should be 1. So let us use the direct formula, because now we know that at which points it is discontinuous. There is only one point, only one possibility of yk, that is 0, and the other place we need to integrate. So so here what we are finding is expectation of this mixed random variable capital X, that is defined as the integration. On the left side it is anyway 0, right? On the left side it is anyway 0. So we need to integrate from 0 to infinity, and among the 0 to infinity, what we are going to do, this is CDF. So first we need to find the probability density function, that is the derivative. And we know that derivative of half and 1 is 0, right? So derivative is non-zero, that means probability density function is non-zero only on this interval, right? And on this interval the derivative of fx is half. So that means we need to integrate only over the interval 1 to 2. What is the expectation? X times the derivative of CDF, right? So that means it is x times the derivative of x by 2 plus probability point time probability at that point. So here the point is 0, so we don't need to find probability at 0, because anyway we have observed that probability is half, but that is not required because 0 times any number is 0. Okay, so now what is the integration of this? That is integration 1 to 2 x by 2 dx plus 0, and then we integrate, so we get x square by 2, x square by 2, x square by 4, right? So we need to multiply by half, so that is x square by 4. The limit is 1 to 2. Correct. What is the final answer? 4 minus 1, that is 3 by 4. Right. So this is one example which we have discussed when we have the mixed random variable, and we found the its expectation. We have found, and again here also the random variable takes on the negative side it is 0, so we have not checked the absolute convergence, right? So we discussed in the last example the maximum of normal random variable, standard normal random variable with 0. So is it continuous random variable or is it a mixed type random variable? So maximum of x and 0, where x is a standard normal random variable. So we have discussed that if we write down its probability density function, on the left side it is 0. On the left side of origin it is 0, and on the right side we get 1 upon root that integration minus infinity to x 1 upon root 2 pi exponential of t square by 2 minus t square by 2. All right, so that last example where we found the expectation of maximum function of x and 0, that example also can be considered as a mixed random variable, and if you find using this method its expectation, you will get the same answer, 1 upon root 2 pi. Right. Pardon? So that is a mixed random variable. For that you need to write down the So you are asking about that maximum example, right? So there you need to write down its CDF first. So we know the CDF of standard normal random variable. So we have denoted that by capital NX, if you remember. So capital NX is what? That is a CDF of standard normal random variable, right? So we know CDF of standard normal random variable. Now we define what is the maximum of the standard normal random variable and zero random variable. So if you know random variable CDF of one random variable, you can find CDF of maximum of random variable, right? So that thing we discussed in earlier class. We have discussed maximum of random variable x and a. What is the CDF, right? So using that you can find the CDF of standard normal random variable and 0, right? So once you write down that CDF of maximum of random variable x, the n01 and 0 function, once you write down the CDF, you will get the you can use it. You need to differentiate it, right? And before differentiating it, you can easily see that that is a that is mixed type. So because on the left side it is 0, on the right side it is not 0, right? On the right side it is not 0. So basically at 0 you will get the discontinuity. You will get the discontinuity, right? So try that example. You will get the same answer. You will get the same answer. Okay, so today's class is essentially regarding the variance and moments. So, so we are given the random variable capital X, and we have discussed that using the given random variable capital X, we can construct new random variables using the linear combination by squaring and cubing, right? So for given random variable capital X, we can find its powers. So expectation of the powers is known as the moments. Is known as the moments. So nth moment of x is defined as expectation of x power n. Expectation of x power n. So let x be a random variable. So expectation, the nth expectation of random variable x is called nth moment of x, and it is defined as by expectation of x power n so we just now discussed what is the expectation formula of the random variable g of x, right? So here we are considering the function x power n, right? So this is also function of x. This is also function of x. So if you have the function of x, that is g of x, we know what is the formula. We know what is the formula. So formula is summation gx fx of x, right? Summation gx fx of x. So here what is gx? That is x power n. So that means gx fx is x power n fx. So that is the formula of the moment, right? So formula of the nth moment is essentially all the possible values in the range where x power n times fx at x. So this is the discrete case, and this holds whenever summation with the modulus sign is convergent. Right, and similarly we can define the continuous case, that is minus infinity to infinity x power n dx whenever. So this is discrete case, this is continuous case, that is summation, the integration is convergent. So we have found expectation of several random variables in the last class, geometric binomial, Poisson. So we have found expectation of x. We can also find expectation of x square, right, for each random variable, each known random variable. And using this moment definition, the next definition is the nth central moment. So nth central moment of random variable x is defined by expectation of the random variable x minus ex power n. So what do we mean by this quantity? So expectation we know of a random variable. That means this should be a random variable if you want to find this, right? So we know that if x is a given random variable, then e of x is a number. Expectation is a number, right? So that number we can consider as a constant function, right? Constant random variable, and that means this is the difference of random variable power n. So we have difference of two random variable, that is again random variable, its power is again random variable, right? So that means here essentially we are considering the function gx to be, so here what is gx? Gx is x minus, now expectation is a mean, so we denote it by mu, right? That is a fixed number. So our function is this one, gx is x minus mu power n, right? So using this gx function we are going to find expectation of this random variable. So now you tell me what is this formula. Gx time fx, where gx is x minus mu power n, right? That is x minus mu power n times fx, where what is mu? Mu is mean. Mu is mean. So again similarly we can easily write down the continuous case, that I will not write. We'll quickly move to the variance definition. So variance of a random variable x is defined by, so variance of x is by definition it is the second central moment. So that is e of x minus mu square, expectation of x minus mu square. So that means its formula will be x is in the range of x, so and x minus, yes. Scroll down, yeah, sure. So here we have this formula. I will provide you notes up in the Google Classroom, right? So in this formula, when we substitute n equals to 2, we get the variance, right? We get the variance in the discrete case. So when we substitute n equals to 2, we get x minus mu square, x minus mu square fx of x, fx of x. So this is our variance, and then the last definition is the standard deviation. Standard deviation is sigma x is defined by sigma x is essentially the of the random variable is square root, positive square root of the variance, positive square root of the variance. So all this definition will coincide with our usual definition of mean, variance, and standard definition, which we studied in school mathematics when we consider the discrete random variable with finitely many outcomes, right? Uniform discrete random variable with finitely many outcomes, discrete uniform. Okay, so let us take some examples and find what is the variance in different cases. So all the example I am not going to do what we have discussed in the last class, but one or two example we'll see today. The first example is the Bernoulli random variable. So if x is a Bernoulli trials with the probability of success is p. Probability of success is p. So in this case, what is our question? Our question is find the expectation and variance of x. So Bernoulli trials means we have two outcomes, 0 and 1. Probability of 0 is 1 minus p. Probability of 1 is p. Probability of success is p. Right? X equals to 1 is p. And expectation is summation x times probability of x equals to x. So here probability of x equals to 0 is 1 minus p. Probability of x equals to 1 is p. Right? So what is the expectation? Expectation is summation x times probability of x equals to x. So in range we have only two values, 0 and 1. So that means this is 0 times probability of x equals to 0 plus 1 times probability of x equals to 1. X equals to 1. So this term is anyway 0, right? That is 0 times 1 minus p is 0, and this term is p, right? So so the mean of Bernoulli trial is p. Mean of Bernoulli trial is p, and when we take p is half, that is exactly our uniform case, uniform discrete case with two outcomes. So now we have mean is p. So what is our variance? Variance of x is essentially summation x in the range x minus mu square fx. fx. So there are only two outcomes, 0 and 1. So x is 0 and 1, and x minus mean is p. Mean is p. So x minus p square, and the probability at x. Probability at x, right? So what we get is 0 minus p square times probability of x equals to 0 plus 1 minus p square, probability at x equals to 1, x equals to 1. So that will turn out to be p square. Probability of x equals to 0 is 1 minus p. 1 minus p square, probability of x equals to 1 is p. So now we can take p into 1 minus p common, right, from the both terms. So what will remain? Remain will be 1 minus p plus p, right? 1 minus p plus p. Okay. So p will cancel out. So final answer is p times 1 minus p. Right? So in the Bernoulli random variable, we have found what is the mean is p, and the variance is p times 1 minus p. P times 1 minus p. Right? Okay. So this was the easy example because only two outcomes, uh, uh, only two values were there in the range of the random variable. So now let us find the variance of the geometric random variable So example, let x to be the geometric random variable with probability of success is p, and the question is find mean and variance of x. Mean and variance of x. Okay, so what is the mean of geometric random variable? That is 1 by p. So that we already found in the last class. So mu we already know. We need to just find the variance. So here mu is 1 by p. That we already know from the last class. We need to find the variance. So variance of x is, by definition, it is summation. So this is a countable discrete random variable with countably many points in the range. All the natural numbers are in the range. So we have the summation k1 to infinity. So the initial formula is x is in the range x minus mu square, probability of x equals to x. So this is our formula of the variance, in which if we substitute the geometric random variable, that means we have the range 1 to infinity. K minus mu is 1 upon p, so 1 upon p square. Probability of x equals to k is p into 1 minus p power k minus 1, right? So that is our geometric random variable probability mass function, right? So now in the last class, when we found the expectation, we came across this term that we reduce up to the next term by taking p outside, and that is known derivative formula 1 minus p power k, right? And then we have switched the derivative and summation, because summation is over k different variable, then p we have switched it, and then the series has become geometric series which we already know what is the sum of the series, and we have solved it. Okay, so so this is not a geometric series, right? So we cannot directly find the sum. So that means we need to do some computation to make it into geometric series, like in the last class, whatever we have done. So here the term is k minus 1, k minus 1 by p square. So that is a quadratic formula. So let us solve it and find the corresponding series. So we get k square minus 2k by p, right? And then we have 1 by p square. So this is a one term. If we separate this as a three different series, then what we will get? We get summation 1 to infinity k square p 1 minus p power k minus 1. That is first series. Second series is minus 2 by p summation k p 1 minus p power k minus 1 1 to infinity plus summation 1 to infinity 1 upon p square p 1 minus p power k minus 1 . So this is a geometric series, right? If you cancel 1p, then that is a geometric series. What is the sum of this series? So that is 1 by p summation 1 minus p power k minus 1 1 to infinity. That is 1 by p. What is the first term? First term is 1, right? Because k is starting from 1 to infinity. K is equals to 1, k minus 1 is 0. So 1 divided by 1 minus 1 by minus p. So so what is the sum of this series? 1 by p square, right? So you just check if I do any mistake. So what is this term? This term we already found in the last class. That is the expectation, right? That is the expectation, and expectation is 1 by p. So let us directly substitute that here. So if we substitute it here, we get this term, the whole term is minus 2 by p times the expectation, that is minus 2 by p square, right? So we know the sum of these two series. So first thing, we have separated this single series as a sum of the three different series, right? And in general, we cannot do that. We cannot do that. We can do that whenever all these three series is summable, right? If sum of each these three series is finite number, then only we can do this. So we have checked that the two series we can find its sum. The first series sum is minus 2 by p square. The second series is 1 upon p square. Now we need to find this sum of this series, but instead of k, that was the expectation in the last class, we have here the k square term. Right? So we will use the same idea of the derivative, but here we have the k square term, so we need to essentially differentiate two times. So let us find sum of this series. So that is, what is this series? This is k square times p 1 minus p power k minus 1. K is running from 1 to infinity. So what the first thing we will do is, it is the derivative formula. For derivative formula, we need k into 1 minus p power k minus 1. Right? So for that, we need to separate 1k. P we can take outside. So that is summation 1 to infinity k times k into this is essentially the derivative of with a negative sign. With the negative sign. So just check if it is fine up to this stage, right? Because the derivative is minus sign, because derivative of 1 minus p is minus 1, right? So that's why we have taken the negative sign. So now k we cannot take outside. So what we'll do? We cannot take k outside, but we can take derivative outside, right? Because k is the number, so derivative will come outside k and outside the summation. So therefore we get p times minus derivative of summation k times 1 minus p power k. Right? Up to this step it is okay. So now we know we have found the expectation in which we added the series, this type of series, but we have k times 1 minus p power k minus 1, right? But now here we have k times 1 minus p power k. We need to settle it, so we will take q outside, right? Q is 1 minus p, we will take outside. So 1 power will take outside, that will make it minus p times the derivative of 1 minus p times summation 1 to infinity k times 1 minus p power k minus 1 or k minus 1. And then we know that this is again a derivative formula. So minus p times derivative 1 minus p times. So this derivative we can switch with the summation. Right? And so if you want, you can write one or two step in between. So I'm doing 2 step at a time. So first you can write as a derivative formula, and then you can switch the derivative and summation. There. So all these things are in multiplication. Okay, and then what is the sum of this series? That is 1 by p, right? We have computed just now, that is 1 by p. So, and this minus we can make it plus. So that is p times derivative of 1 minus p times derivative of 1 by p, derivative of 1 by p. So what is the derivative of 1 by p? That is it correct, this summation? Just 1 minute. So first term is 1 minus p divided by 1 minus p. Okay. So because here summation is starting from 1, and the power is also starting from k. So 1 minus p by p, so that is 1 by p minus 1. And then we differentiate, what we get. This term will become, the derivative of this is minus 1 by p square. So that is minus 1 by p square, and then we divide by p square. What we get is we get p minus 1 divided by p square. So this function we need to differentiate with respect to p, and so what we will get is minus 1 by p square minus 2 times this, so plus 2 by p power 3. So what is the final answer? That is minus 1 by p plus 2 by p square. So just check once later also if I am doing any plus minus mistake. Right? So go back and just check every step. And what is the final expectation? Expectation is minus 1 by p plus 2 by p square, and we need to add that two terms. So the first term is 1 by p square, and the second term is minus 2 by p square. So this term will cancel out. So final answer is 1 minus p divided by p square. So this is not the expectation, this is the variance. The variance. So I think earlier I wrote variance, right? Okay, so we have found the expectation of the mean and variance of the Bernoulli and the geometric random variable. So one example I am giving as an exercise that you try, that we have the uniform continuous random variable over the closed interval AB, right? So you find what its mean we already found, that is a plus b by 2. If it is over the interval AB, it is a plus b by 2. What is the variance? Variance of the continuous discrete random variable. Okay, so I think that is enough for today class. If you have, okay, thank you. So